Hello everyone, so I wanted to go over and make a video solution to homework 6 from my heat transfer class. If you're not taking my heat transfer class, this is still useful because we discuss concepts like heat flux, heat transfer by convection, heat generation in two different coordinate systems, mainly Cartesian and cylindrical coordinate systems. So let's take a look here at the first question. If you'd like, now is a good time to pause the video to read the question. So here we have a plain wall, and it's made of two materials, material A and material B. Material A has some sort of electrical heating inside of it that's generating heat. And this electronic heater has a uniform heat generation rate that's given in the problem. Now, material B is just a regular solid material, has a certain thermal conductivity, and basically the heat is generated here, passes through material B by conduction, and then into the water by convection. And the problem asks us to find temperatures T0, T1, and T2. And by the way, material A is completely insulated on one side. So basically that means that there's no heat transfer on this side. Think of it as adiabatic wall. It's basically what it is. So typically what's done in these types of questions is to use a thermal circuit. Now the thermal circuit can be used in this problem, but we're going to have some issues here in the wall where there is heat generation. And it's just because the heat generation causes some issues, and it becomes a little bit more difficult to use the thermal circuit in that specific region. So what I typically do is I'll draw the thermal circuit basically from where the heat generation ends. In other words, basically where there's no heat generation forward. So basically what I've done here is I've drawn the thermal circuit from here. So we have here heat transfer by conduction, and then heat transfer by convection into the water. We're going to deal with the heat generation part later. So what I did to basically represent heat generation is I used a current source. We'll get to that in a moment. Before we go on, I would like to make a statement on notation. So I borrowed the picture here is from the Increpera heat transfer textbook. I just changed the numbers. I changed the question a little bit to make it a little bit more different. The notation that I like to use is basically the same as Increpera's notation, and that's because I learned heat transfer that way from that textbook. So let's just go over it real quick. So little q is rate of heat transfer, which is basically watts. Now heat, right, by itself, if you just say the word heat, this corresponds to energy. In other words, capital Q is basically your energy, which is joules. Okay, that's heat. Now rate of heat transfer is power, hence the unit of watts. So the analogy I like to use with my class is that power is, in other words, energy is the same thing as money. So power is basically the derivative of energy with respect to time, which you can think of it as the derivative of money with respect to time. In other words, your power is how your money changes with time. If your money increases with time, you're gaining power. If your money decreases with time, you're losing power. So I think of power as the time rate of change of your money. I find it's a pretty good analogy. I didn't make it up. I got it from my PhD mentor. So if you take a look here, Q by itself is power, it's watts. Another very common unit that's used in heat transfer is flux. Now flux, Increpera notates it as Q double prime. Q double prime is basically units of watts per meter squared. So that's called flux, or rate of heat flux is another way that it's referred to. Another common one is Q prime. This is what Increpera calls watts per meter. So the double prime, I like to think of it as the exponent of the meters in the denominator of the units. So for example, double prime means watts per meter squared, 2 primes, right? 1 prime is just watts per meter. Now, the notation changes a little bit in the Incropera textbook. And for watts per unit volume, or watts per meter cubed, Q dot is used. So please don't confuse. Q dot is not the time derivative of Q. Okay? I know that it's very common. For example, m dot, right? M dot is the derivative of mass with respect to time. And it's very commonly used with a dot to be the time derivative. But in this particular case, Q dot is not time derivative. It is rate of heat transfer per unit volume. Okay, that's just a notation in this textbook. Other textbooks use different notations, and that's fine. There's nothing wrong with the notation you use. I always tell my students, pay attention to the units. The units never lie. Okay, the units will always tell you the truth. Okay, notation, everyone has different notations, but pay attention mainly to the units. And with heat transfer, I'm very careful to make sure I write down all my units to make sure I don't get confused. This particular homework assignment requires you to be comfortable with the units and sort of converting between these different ways of writing the heat transfer. So, in this particular problem, you are given Q dot. Another thing to note is that thermal circuits are typically drawn with Q, not Q dot, not Q double prime, with Q. Now, there are some people that do thermal circuits with Q double prime, and we could do that, but you have to basically modify your thermal resistance equations. So I'm going to just start with the most common way of writing a thermal circuit, and I'm going to show you how to modify it so that you can basically use it in the way that's easiest for the particular problem that you're doing. So step 1 here is to figure out what you can use and what you cannot use. So they give you Q dot, which is basically Q per volume. So I just want to write that down. So just ignore what I have, my little bullet points here. Just ignore that for now. So Q dot. What is Q dot? Q dot is Q watts per volume, which is meters cubed, so watts per meters cubed. So basically, if I want Q, I can just take my Q dot and multiply by volume, right? Which would be great. Then we can just use Q and then it's done deal. Now the problem is that they don't give us the volume. Now this particular geometry is supposed to be Cartesian or like a rectangular geometry. So if you want to draw it in 3D, you can, I'll try to draw the laser pointer here. Basically you have, something like this, and then if you want to draw like the inside, something like this, right? So the volume of this thing is going to be this area here times the length. And I'm talking about, because when you're doing the volume for Q dot, it has to be the volume of the material that is generating heat. So I'm specifically focusing on material A. So it's going to be this cross-sectional area times this length. That's your volume. Now, that would be great. They don't give you the cross-sectional area though. They do give you this length, which is fine, but they don't give you the cross-sectional area. So you can't really find Q. So I just want to break this down a little bit. So volume is what? It's the cross-sectional area times that length, right? But they don't give you the cross-sectional area. They just give you the length. So let's see what happens. Let's do something different. Instead of multiplying by volume, what if instead I multiplied by the length? What is that going to do? So remember, Q dot is what? It's Q per unit volume. The volume was the cross-sectional area times the length. Now I'm multiplying that by the length. That kills this length in the denominator, And we're just left with Q over A, which is, of course, our flux. It's Q double prime, watts per meter squared. So basically, if I multiply by the length, I can write things in flux, in other words, watts per meter squared. That is going to be the most useful way to solve this problem. So let's actually do that. So Q double prime is going to be our Q dot times the length of the material that's generating heat, which in this case is material A. So Q dot is they give it to us 1.2 times 10 to the 6 watts per meter cubed. I multiply that by the length of material A, which is 40 millimeters, so 40 times 10 to the minus 3 meters. So we're going to get here 48,000 watts per meter squared. Okay. That squared is a little bit illegible. Let me fix that. Okay. Now, I need to play with this a little bit so that I can use, because I can't use Q, but I can use Q double prime. So remember, this circuit is an analogy to the heat transfer. So we're basically using the circuit in a way like a map or as a tool to help us analyze the heat transfer, because if we use a circuit, heat transfer becomes so much easier because it's just a series circuit. So it turns out that the current Q in this circuit, if you look at it from the perspective of a circuit, is this voltage, right? Which in this case, this voltage would be corresponding to T1. This voltage corresponds to T infinity. So T1 minus T infinity, if I take T1 minus T infinity, divide by the total resistance, I should get the total current. And because it's a series circuit, it's the current Q. So basically, it turns out that Q is what? It's T1 minus T infinity over the total resistance, which is basically the conduction through material B times the convection, right? So I drew the circuit intentionally so that thermal resistance here corresponds to heat transfer by conduction through material B. Thermal resistance over here corresponds to the heat transfer by convection from material B into the water. There you go. Now, let's just expand the denominator a little bit. For Cartesian coordinates, thermal resistance due to conduction, basically the length of the material, in this case it's material B, divided by thermal conductivity KB times the cross-sectional area A. Convection is going to be 1 over heat transfer coefficient H times A. There should be a plus here. Now, we're assuming that the cross-sectional area is the same everywhere. So I drew for you here my little rectangular prism, right? It looks something like this. Right? So the cross-sectional area is the same for this part, for this section and also for this section. So it's the same surface area everywhere. So that A is the same here and here. So I can take that out as a common factor. Let me just make a little room here. So watch this. You get this. Now, I'm going to put some parentheses here just to illustrate this point a little bit. But basically, what we have here is 1 over 1 over A. Just focus on this portion, right? 1 over 1 over A. It's the same thing as if I were just to take this and put A on the numerator, right? So I can do that. So let's actually go ahead and do that. So Q equals A, T1 minus T infinity, over L for the material B over KB plus 1 over H. Now, what if I just divide both sides by area? Divide by area. Divide by area. This goes away, and what do I have over here? I have flux. Exactly what I'm looking for. So basically, Q over A is Q double prime. L subscript B over K B plus 1 over H. And this is the equation that's going to help me solve this problem. Okay. Some people, as I said, will draw this circuit in terms of flux, which is actually what I've done over here. Okay, if you draw everything in terms of flux, you do have to modify your thermal resistances to look like this. Basically, your thermal resistances are going to not have the A here in the denominator. So sometimes I've seen it in some textbooks that some people will call this, you know, R conduction B, and they'll call it double prime, just sort of to match the notation here, so you know, so it makes sense. Basically, all that's happening is that you're missing that area on the bottom there because the area is already included here. Okay, so I did the algebra for you. You can take a look and see that that's where the area has gone. Okay, so it's a little bit of a mathematical manipulation. So I redrew the circuit using the flux parameters just to make it a little bit easier to work with. And now we're basically going to work backwards to find this temperature and this temperature. Once we got those two temperatures, then we can worry about this heat generation region and ultimately this T0. So again, we're going to use this circuit equation. T2 being this voltage from here to the ground, you can think of it, and T infinity is from here to the ground, right? So if I do T2 minus T infinity over this resistance, I should get my current. So I know my current, I just need to find T2. So basically, let's write the equation. So basically, Q double prime is T2 minus T infinity over the thermal resistance, which is 1 over H. And I know my Q double prime, I know my T infinity, I know my H, so I can just solve for T2. So we'll just do a little bit of algebra, solve for T2. Now, I always recommend this to my students. Try to do the, I shouldn't say try, do the algebra in as many steps as you need to make sure that you don't make a mistake. Right now, I'm skipping some steps, and it's just because I want to save time and I want to save some space on the paper. But if I'm working out a problem, you know, for a serious situation or you know, something that I need to have something very correct, I will take as many steps as necessary to make sure I don't make a mistake. And I recommend that students do that too. Anytime that you try to do stuff in your head, there's a likelihood that you might make a mistake. So take as many steps as you need. What matters is that you get the right answer. Okay. So we solve for T2. So Q double prime here is your, we found it earlier, was the 48,000 watts per meter squared. Divide by 500 watts per meter squared Kelvin, that's your H. Plus T infinity, which is the ambient temperature. Now you could, if you leave it in Celsius, you will get the answer in Celsius. Now, some of the equations in heat transfer require you to have stuff in Kelvin, like, for example, the radiation equation. So I always recommend you just do everything in Kelvin. At the end, you can convert to Celsius. So if you do this in Kelvin, you'll get 389.15. In Celsius, that translates to 116 Celsius. So that's your T2. T1, we can do the same thing, right? Because now we have this guy. So now we can do this voltage and this voltage divided by this resistance, right? And from there, we can manipulate the algebra to get T1. So same concept where the current, let me use, okay, current is going to be T1 minus T2. And we divide by the thermal resistance like so. And now we can, we have everything. We just need to find T1. So you, again, do the algebra to find T1. Plug and chug, and you get your T1. Length of material B is the 25 millimeters. Let me just make sure. It is correct, millimeters, good. K is 100 watts per meter Kelvin. And we add this to the T2 that we found earlier, like this. I'll put it in Kelvin. It's supposed to be a K. So T1 will turn out to be 401.15 Kelvin again, which basically turns out to be 128 degrees Celsius. There you go. So now we've sort of reached the extent of the thermal circuit model. Now we have to sort of talk about heat generation. So because of the fact that we have heat generation in material A, which is this material over here, we cannot use thermal circuit in the same way. We have to actually use an equation that we developed in class. So the equation is developed specifically for Cartesian coordinates. And basically you're going to get a function of the temperature inside that material that generates heat. So it's going to look like this. This is the equation we generated, or not generated, but we derived in class. So K is thermal conductivity of material A plus T0, where T0 is going to be that temperature right here. Right here, this temperature right here. So basically the shape of the temperature distribution is it's like parabolic, okay? So that equation basically gives you the temperature as a function of the parameter x, the length, okay? So the idea is we know the temperature T1. So basically we know the temperature at T of x equal to LA. That's temperature T1 right here. And we can plug that into the equation and then solve for T0, which is the max temperature basically. So right? So basically we're going to plug in x equal to LA. I put in here LA, and then I can move this to the left-hand side, and I got my T0. So let's just do it here. So T of x equal to LA minus Q dot, this should not be x, this should be LA, over 2 Ka plus T0. So now I can just, and by the way, what is T at x equal to LA? Oops, let me just move this over here like this. T at x equal to LA is actually T1. We just solve for it, so we have that number. So now we can just solve for T0. So T0 is basically going to be what? It's going to be T1 plus Q dot LA squared over 2K sub A, like that. So now we just plug in our numbers and we're basically done. So we can solve for T0. So here we go. So I'll just write it one more time so that we have it. Like this. Okay, so let's plug in our numbers, and there we go. So T1 is 401.15 Kelvin. Q dot is 1.2 times 10 to the 6 watts per meter cubed. LA is the length of material A. Again, this equation corresponds only to the material that generates heat, which is material A. The length is 40 millimeters. divided by 2, thermal conductivity of material A is 70 watts per meter Kelvin. So then the T0 is 414.86 Kelvin, which is basically 141.71 degrees Celsius. Another thing I like to tell my students is to ask themselves if the answers that they got make sense, right? So if you think about it, right, this material is generating heat, and then here is water that's colder, right? We'd assume that this is the highest temperature, this is slightly lower, this is lower, right? So let's see if that makes sense. So the temperature T0 is the highest temperature at 141 Celsius. T1 is a little bit less at 128, and finally the temperature near the water is 116 Celsius. So it makes sense. Okay, let's take a look at question number 2. So this is a power cable question. So again, I would pause the video just to read the question itself. Basically, in this question, you have an electrical power cable where you have here the conductor, and then you have an insulation on the cable. And the power cable is 5 meters long, and they tell you that you have a heat generation rate inside the power cable. This is specifically in the conductor, right? Because the current is flowing in the conductor, so that's where your heat is generated, in the conductor. Okay. They give you the parameters. They say that the insulation is 0.4 centimeters thick. They give you the thermal conductivity of the insulation. They say the cable is surrounded by air at 20 degrees Celsius. Okay. In this part, I was nice. I said that the combined heat transfer coefficient. So I basically combined the effects of convection and radiation into one heat transfer coefficient, just to make it a little bit easier. I just gave you the combined one. Okay. So we're asked to calculate the temperature right here, Ti, at the interface of the cable and the insulation, and also the temperature at the center. Additionally, they want you to calculate what is the current flowing in the cable. So the most important calculation in this problem from an engineering aspect is the interface temperature. In other words, the temperature at the conductor, basically as the conductor touches the insulation right here, because that is where the cable will start to burn if the current is too high. So this is a real world problem where this is an important number to calculate. So let's see how to do that. So in this particular question, you could actually find Q. Before we get to that, let's take a look at the thermal circuit. So thermal circuit, very similar to what we did in the previous problem. It's almost actually identical. Basically, you have this portion here, which is heat generation. So you can't really use the thermal circuit there. What I did in both this circuit and the previous circuit is I represented the heat generation, I represented it as a current source, which is basically what it is. It's providing energy, it's providing heat. Okay. In this portion here of the insulation, you can use the thermal resistance due to conduction, and on the outside with the air, thermal resistance due to convection. Now here, this thermal resistance combines the effects of convection and radiation, so you don't have to add like a radiation thermal resistance in parallel. It's all, I made it so that it's all in one. So this problem is the thermal circuit's almost identical. The only thing that changes is the geometry. You have to be a little bit careful here. Now, here's some good news though. The good news is that you can actually find Q. So you don't have to do any of the Q double prime stuff. So why can you find Q? Because we can find the volume of the conductor, right? So the volume of the conductor is what? It's the surface area here of the circular part times the length of the conductor. So we have the radius of the conductor, and we also have the length of the conductor, so we can find the volume of the conductor. Again, it's the volume of the conductor because that is where the heat generation is taking place. So recall that Q dot is just the Q per unit volume. So Q is basically going to be Q dot times volume. The volume of the cylinder, again, is going to be the area of the this part, this area, which is the cross-sectional area of the conductor. So pi r of the conductor, so r1 squared, times the length of the conductor, which is just L. And let me actually put them all in parentheses like this. So we can plug in our numbers and get a value for Q, which is great. So Q dot is 1.91. Here's 0.5 times 10 to the minus 2 because it's centimeters. And I like to alternate square brackets and regular parentheses, just easier on the eyes. Okay, so we got this. And we should get that Q turns out to be 750.055 watts. You might notice I carry a lot of decimal places for the in-between steps, but at the very end, I will truncate to the correct decimal places. I like to carry decimal places just in the in-between steps to avoid the rounding error. So at the very end, when you report your final answer, that one you can truncate. So let's find the interface temperature. In other words, temperature right here between right at the conductor insulation interface. So what you can do is exactly what we did in the previous problem. This temperature corresponds to this voltage. This temperature corresponds to this voltage. So Ti minus T infinity divided by the sum of the total resistances. That's going to give you Q. And we actually have Q, so we can basically manipulate that equation to get Ti. So Q is going to be, again, Ti minus T infinity over R1 plus R2. Okay, so we can, again, do some algebra, and we find that Ti is basically Q times R1 plus R2, and then we add the ambient T infinity to that. So R1 is the conduction thermal resistance for the insulation. This time it's going to be a little bit different because it's a cylindrical geometry. Before it was L over Ka because it's Cartesian coordinates, but in cylindrical it's going to look different. You're going to have like a natural log in there. We got natural log, and we got to take the outer radius divided by the inner radius. And I'll explain exactly what those radii are. Divided by 2 pi K of the insulation times the length of the cable. The R2 is basically it's like your convection thermal resistance, except now that H is basically holding both the convection and radiation together. So it's going to still be 1 over HA, like this. Now A, right, is the surface area that is corresponding to convection and radiation. So that surface area is basically this surface area of the cable, right? So I think of it, if you, right, you're just taking this, I call it the soda can surface area. Basically, if you have a soda can, right, the surface area that corresponds to the label of the soda can is your surface area. So basically it's going to be, if you unwrap the soda can label, it looks like this, right? Where this distance corresponds to the circumference. So it's basically 2 pi r times the length of the cable. Okay, so it's basically 2 pi RL. So it's going to be 2 pi r, but this r is the overall radius of the whole thing. So that's R2 times L, or the length of the whole power cable. So it looks something like this. Okay. R2, they didn't give it to us directly. They sort of wanted us to think about it a little bit. They said that the thickness, in other words, this distance of the insulation is 0.4 centimeters. They do give us R1, which is 0.5 centimeters. So from here all the way to here is 0.5 times the thickness, which is 0.4, so it should be 0.9 centimeters. So now we're just ready to plug in our numbers and solve for T infinity. So let's go ahead and do that. So let me just want to make sure. Okay, now we have room here. So Ti Q is 750.055 watts. We have here natural log. R2 is the 0.9 centimeters. Make sure that this is as legible as possible. The R1 is 0.5 centimeters. 2 pi times K of the insulation, which is 1.2 watt per meter Kelvin, and the length of the power cable is 5 meters. Here we go. H, combined radiation and convection, is 200 watts per meter squared Kelvin. We have here a 2 pi. R2 is 0.9 centimeters. And L is the length of the cable, which is 5 meters. T infinity is the ambient, which is 20. In my notes, I left everything in Celsius, but for the sake of this video, to keep things consistent, I'll put things in Kelvin. So when you work all this out, you'll find, first let me put it in Celsius and I'll convert to Kelvin. You get 164.33 Celsius. So in Kelvin, 164.33 is going to be 437.48. So 437.48. Okay. So that's the interface temperature. Now, if you're familiar with cable ampacity ratings, this is why I put Courage over here getting upset, because this temperature is most power cables burn at around 90 degrees Celsius. The insulation usually burns around 90 degrees Celsius in general. There are, of course, power cables that can handle higher temperatures, but most power cables are around 90 degrees is sort of like the maximum temperature that they can handle. So this temperature is way too high. So a couple things can be done. Either you switch out the power cables to bigger ones where the heat transfer will be basically you'll have lower temperatures. That might be expensive. Another thing you can do is install some sort of cooling. So maybe you can put some fans or something, or maybe install the cables in some sort of oil or water or something like this to cool down the power cable. Additionally, what you can do is also run less current through the power cable. So you have to basically reduce the current. That'll reduce the temperature of the power cable. Now, to find the temperature at the very center of the power cable, right here, again, it's a heat transfer. It's an equation that we derived in the classroom. So that equation looks something like this. So I'm just going to take it right from the textbook. It's a function of the radius. And it looks like this. We will need to make some small modifications to this. So the K, thermal conductivity here, is going to be the thermal conductivity of the copper. Let's make these brackets like this. Okay, so let me just draw the picture that this corresponds to. So basically, this equation is derived for a cylinder that looks like this, typical cylinder, where the temperature right here on the surface is Ts, and the radius of the cylinder is, they called it R naught, or R sub 0, like this. So we have to make some modifications because basically for our problem, the cylinder is corresponding to the conductor. So R0 or R naught is corresponding to the radius of the conductor. And then TS, what they call TS, is actually what we call TI. It's the temperature right here on the surface of the conductor. So we have to make some adjustments. So I'm just going to note that. So we modified, this guy should be modified. Modify this to be TI. The R naughts, of course, also have to be modified because the radius of the conductor is not R naught. They called it, in this problem, it's called R1. So these, let me make that a little bit more legible. Modify to be R1. Okay, let's go ahead and do that. So we get now T of R is Q dot R1. It should be R1 squared over 4 times thermal conductivity of the copper, 1 minus R squared over R1 squared plus Ti. So we want to find the temperature at R equal to 0. In other words, right at the center of the conductor. So let's go ahead and do that. We basically have everything, so we can just plug and chug. So T at R equal to 0, that's going to be our T0. And you know what? I'm just going to plug in all the numbers just straight away just to keep things a little bit faster. Again, if you need to take extra steps, take the extra steps. No one's judging you about how many steps you take. People only care if you get the right answer. So Q dot is 1.91 times 10 to the 6 watts per meter cubed. That's your Q dot. R1 is the radius of the conductor, which is 0.5 centimeters. We got to square that. Divide by 4 times the thermal conductivity of copper, which in this problem is given to be 15 watts per meter Kelvin. Now this portion in the parentheses, we have R equal to 0, right? So this is just 0, so the whole thing in parentheses is just 1. So basically that vanishes, we just have this. And then Ti, we found it previously. Ti is the 437.48 Kelvin. Okay. So again, the answer that I have reported, I have it in Celsius, but I will find it right now for you in Kelvin. So 165.13 plus 273.15. Okay. So 438.28. 438.28. And of course, that's this is the Kelvin. Okay. All right. So let's go for the last part. The last part asks you to find the actual current. So this is actually not too difficult. Basically, the Q, right, which we solved for it. The units of Q are watts. Now think about it. When an electrical power cable, when you have current flowing through a power cable, what happens? It heats up, right? So that heat, that energy, that's basically your heat energy, right? So if you were to calculate the rate at which that energy is dissipated in the power cable, that's your Q, which is watts. Q is watts, watts is power. So basically Q is quite literally equal to the electrical power that's dissipated in the power cable. What is power? It's I squared R. I squared times the resistance. Now they give you the resistance of the conductor, but they don't give it to you in ohms. They give it to you in ohm per meter. So maybe what I could do is I can write this in a different color. They give you resistance, and I'll put the subscript ohm per meter. So in order for this equation to work, you need the resistance in ohms. So you need to multiply by the length of the power cable. Now, this thing in parentheses will be in ohms. So this thing will basically give you R in ohms, and then all is right with the world. Everything makes sense. So basically now, you just solve for the current. So let me just write it one more time. So Q is going to be I squared times R in units of ohm per meter, like so. And now I can solve for I. So I is Q per resistance in units of ohm per meter times length L. And this whole thing needs to go on a square root. And there you go. So let's plug in the numbers. Actually, I can plug them in here. So Q is 750.055 watts. They give you the resistance ohm per meter. And again, this is not just because they want to be mean or anything. This is actually typically how it's done in the field. They'll give it to you actually in ohm per meter, because then, depending on the length of the power cable, you can find out what the resistance is. Okay, so this is 6 times 10 to the minus 4 ohm per meter. Multiplied by the length, in this case it's 5 meters. And then we take the square root. This should give you 500.02 amps. And we can just truncate that to 500 amps. Done. The last problem is a fin problem. And in this problem, I'm going to switch gears and I'm going to use the method that's in the Sengel or Sengel heat transfer textbook. I'm not sure how to pronounce it. If you know, please let me know. Correct me if I'm pronouncing it wrong, if it's Sengel or Sengel. I'm using the method that he uses in the textbook. So here is the rectangular fin, and they say calculate the efficiency and the rate of heat transfer for the rectangular fin shown below. So the method that's outlined in this textbook is they use the concept that basically if you were to plot as a function, like imagine your fin, imagine the fin is like this, right? And what you're going to do now is you're going to plot the temperature of the fin as as a function of the length of the fin. So let me just draw that one more time with the laser pointer. Here's the fin, and you're plotting the temperature with respect to the distance. Okay. Temperature right here is the temperature of the base of the fin, whatever that is, right? And if you have a perfect fin, which doesn't exist, if you have a perfect fin, the temperature is the same across the fin for the entire length of the fin. That's not what really happens. In reality, the temperature of the fin actually drops like this. Okay. How much it drops will determine whether or not it's a good fin or a bad fin. So a good fin will have less of a temperature drop than a bad fin. Bad fins will just drop a lot. Okay. So the idea is we can calculate the Q, if it were a perfect fin, the ideal fin, imagine like it's just the same temperature, T of the base, across the entire fin. We can calculate that ideal fin. And then using some equations that are given to us in the table, we can calculate the efficiency of the fin. So basically the efficiency of the fin is going to be the real heat transfer of the fin divided by the ideal heat transfer of the fin. So if I find this and I find this, I can find the real heat transfer of the fin. Sort of an indirect way, but it's actually quite clever and quite convenient. So let's actually solve it that way. So this page is taken directly from this textbook, and the efficiency for a rectangular fin following that particular method, you have to use these equations here to calculate the efficiency. Now, the efficiency here is you need hyperbolic tangent. Most scientific calculators should have hyperbolic tangent as a function in the calculator. If you don't have it or don't know how to access it, hyperbolic tangent can be written with exponentials like so. So I just provided that in case you don't have access to that on your calculator, or you don't know how to access it, chances are most modern scientific calculators will have this. So take a look. Okay. Let's go ahead and solve this. So we basically need to find a few things. We need to find this constant m that they call it, and LC. LC is a corrected length. I wrote here a little note. LC is called the corrected length for a fin with an adiabatic tip. I don't want to get too much into the derivation of this formula. It's quite complicated, but this is there's several ways that you can view fins. And depending on the type of calculation you're doing, one is more accurate than the other. For now, we're going to use the adiabatic tip version, which is the version that's used in this method. So we're going to need to find the corrected length and this constant m. It's really just following the procedure. So the corrected length is basically the length of the fin plus the thickness of the fin divided by 2. So just, excuse me, plug and chug. So 2 centimeters is the length of the fin, and the thickness is 0.3. And okay, corrected length will turn out to be 2.15 times 10 to the negative 2 meter. M is going to be 2 times h, which is the heat transfer coefficient of the air or fluid or whatever that's passing over the fin, divided by thermal conductivity of the fin, okay, times the thickness of the fin, everything square root. So plug and chug. There should be a 0 here. Okay. So m, if you look at the units carefully, the units will be 1 over meter. Okay, 1 over meter. So when you do m times LC, which is ultimately what you're going to plug into the hyperbolic tangent, m times LC is basically meter times 1 over meter, so it basically is unitless, which makes sense because ultimately your efficiency should be unitless. Okay, so it all works out. So m times LC looks like this. Here's m. Has units 1 over meter. LC has units just meter. As I said, always pay attention to units because they will never lie to you. Okay, here's your m times LC. Now you plug that into the hyperbolic tangent. Again, if you have a scientific calculator, if you know where that function is, you can just go right ahead and use it. And you will get your answer. It turns out that, so I predict one of the questions will be, oh, should I be using degrees or radians? It actually turns out that it will give you the same answer regardless of if you use degrees or radians. Okay, if you prefer not to use the function in your calculator, or let's say you don't have it or you can't find it, if you have an exponential function, this is the exponential version of hyperbolic tangent. You could just do it this way. Okay. So when you plug this in, your efficiency should be 0.93614. So basically 93.67%. Okay, not bad. So to find the actual heat transfer of the fin, we need to find the ideal, or it's often called the maximum heat transfer of the fin. So basically, you're just going to use Newton's law of cooling. So Q max, because it's all convection, so Newton's law of cooling is what applies. You have H times the area of the fin times, normally Newton's law of cooling is Ts minus T infinity, but Ts in the perfect fin, the surface temperature of the fin everywhere is going to be the same as the base if you assume perfect fin. So it's just going to be TB minus T infinity. So let's go ahead and do that. Now the area of the fin, if you want this to be accurate to this method, you need to use the area of the fin that they define here. So the area of the fin they define here is 2 times the width times the corrected length. So 2 times the width times the corrected length. Just as I said, for the sake of time, I'm not going to go into the whole derivation of where these things come from. It is in the textbook. If you want to take a look at the textbook, it's given there. But that's what it turns out to be. So let's go ahead and do that. So the area is going to be 2 times the width times the corrected length. And we have here temperature of the base minus T infinity. So Q max here is H. The width of the fin is 1.5 times 10 to the minus 2. Corrected length is 2.15 times 10 to the minus 2. TB is given as 40 degrees, and you know what? I just to keep my brackets. Okay. And the T infinity is 20 degrees Celsius. If you're wondering why I didn't convert these into Kelvin, it actually doesn't matter, because when you do a temperature difference in Celsius, it's the same as temperature difference in Kelvin. So you're going to get the same number, regardless of what you do. Here comes Q max, so it should be 2.58. So finally, your fin efficiency is basically your real heat transfer of the fin divided by the ideal or the maximum heat transfer of the fin. So just solve for Q fin and you're done. Here comes the efficiency of the fin. Let me just make sure I had this right. 0.936714. Good. Q max 2.58 watts. And you should get that Q fin is 2.42 watts. And that's how you solve this one.